This session introduces the concept of the gradient. And to define gradient, we need to specify a scalar function or a scalar field, and then apply the gradient operator or the del operator to this scalar function or scalar field. Definition. So let phi, which is a function of x, y, and z, be a scalar function or you can say scalar field. Then the gradient of phi denoted by or you can write it as it's defined by gradient of phi equals to partial x partial y partial z actually the definition of the del operator. Then you put phi here, which reduces to partial phi partial x plus partial phi partial y plus partial phi partial z. Okay. So this is how we define the gradient of phi. So note that gradient of phi is a vector or simply a vector quantity. So once we have defined the gradient of phi, let's do some examples. So given if phi is given by 4x cubed y sine z, find gradient of phi. So solution, by definition, we have grad phi given by So we'll have partial x of this function 4x cubed y sine of z, partial y of 4x cubed y sine z, j, plus partial z 4x cubed y sine of z, then k. Now this function differentiated partially with respect to x will give us 12 x squared y sine z and then plus, if we differentiate this partially with respect to y, we get 4x power 3 sine of z j. So this function differentiated partially with respect to z will give us 4x power 3 y cos z. So this is the solution for the gradient of phi for that given scalar field or scalar function. Problem number 2. If phi of x, y, z is given by 3x squared y minus y cubed z squared, find gradient of phi at the point 1 minus 2 minus 1. Solution. We know that gradient of phi is partial phi partial x I plus partial phi partial y j plus partial phi partial z k. So which means in our case, gradient of phi, now when you differentiate this function with respect to x, so this first term will get 6xy, second term has no x, so 0, plus first term in this function, when you differentiate with respect to y, we get 3x squared. Second part will get minus 3y squared z squared. So this is the component of the j vector, plus this function, when you differentiate with respect to z, first term will be 0 because there is no z variable here. Second will give us negative 2y cubed z, and then this will be our k. So which means that the gradient of phi at the specified point 1 minus 2 minus 1 be given by, so remember when you are given coordinates in this form, this is x value, this y value, and this is z value. So where there's x, you replace by 1, where there's y, you replace by minus 2, where there's z, you replace by minus 1. So we'll have 6 times 1, and then y is minus 2, I plus 3x is 1 squared, minus 3, y is minus 2 squared, z is minus 1 squared, j, and then minus or plus. So I'll have minus 2 into y is minus 2 power 3, z is minus 1, and then this k vector. So which will give us 6 by 1 by negative 2 will give us minus 12 I plus, so this will be 3 minus, so minus 2 squared is positive 4 times minus 1 squared is 4 times minus 3 is minus 12 j, and then plus this is minus 2. So minus 2 power 3 is minus 8 times minus 1 is positive 8 times minus 2 is minus 16. So in simplification, you get minus 12 I, 3 minus 12 is minus 9, then minus 16 k. So therefore the gradient at the specified point for this scalar function is given by minus 12 I minus 9j and then minus 16k. Example 3. If phi is given by x cubed y plus x y squared plus 3y, find, so part 1, gradient of phi, part 2, gradient of phi at the point 1 0 0 0 0, and then number 3, the modulus of gradient of phi at the point 1 1 1. So in this case, solution, by definition, gradient of phi is given by partial phi partial xi plus partial phi partial yj plus partial phi partial zk. This by definition. Now our phi function, when we differentiate with respect to x, first term will give us 3x squared y plus second term will be y squared, and then this last or third term will be 0 because this is x. So I, first term will give us, with respect to y, x power 3. Second term will be 2xy. Third term will give us positive 3. So j. And then there is no z term in this phi. So the component of k will be 0. So this is the first solution. And then the second solution, gradient of phi at 0 0 0 means we replace where there's x, y, and z each by 0. So we'll have 3 0 squared 0 plus 0 squared I plus 0 power 3 plus 2 0 times 0 plus 3 j, and then plus 0 k. So when you work out this one, you get I component will be 0, j component will be 3, and k component is 0. So which can just be written as 3j. Now the next part is to find the modulus of the gradient or magnitude of the gradient of phi at 1, 1, 1. The first thing you have to define the value of the gradient at 1, 1, 1. So Roman 3, first gradient of phi at 1, 1, 1 will be given by 3 times 1 squared times 1 plus 1 squared I plus 1 power 3 plus 2 times 1 times 1 plus 3 j and then plus 0k. So which will give us, so this will be 3 plus 1, which is 4. I, this 1 plus 2 plus 3 is 6. And then plus 0k. Now, we know that if we have a vector A of the form A1I plus A2J plus A3K, then magnitude of this vector is simply given by the positive square root of A1 squared plus A2 squared plus A3 squared. So this means that the gradient, the magnitude of gradient of phi at 1, 1, 1 is simply given by the positive square root of 4 squared plus 6 squared plus 0 squared, which will be 4 squared is 16, 6 squared is 36, to be square root of 52. Which can be written as 2 root 13. This will be the final solution to the third part of the problem. So that is how we solve some problems on gradient where we have been given the value of the scalar function phi, and then you may also be asked to find the values of the gradient at specified points, as we have seen in these examples. So in the next session, we will also give more computations involving the gradient of a scalar field. Thank you.